Hi, good morning, everybody. We're gonna finish up the chapter and finish up the semester today. And well, actually, both of the remaining sections pretty much reiterate what we've talked about in the last chapter and in section 1 of this chapter. So it's gonna be a lot of repetition, it seems like. So we're looking here is section 2 does testing a claim about a proportion P, a population proportion. We're also going to look at a couple of what's using the B value method. The critical value method. And confidence interval. This is what we've been doing all along, actually. So this again, there's not much news going to be here. Okay, remember, when we talk about P, we're talking about probabilities. And they could be decimals or percents. Because we can convert between any one of those. So the first thing we're going to talk about. Finding the number of successes. Why is that important? Is because when we deal with proportions, we have to know how many successes, how many failures we have. What proportion of the sample is satisfying or not satisfying our experimental conditions. So the number of successes is going to be represented by the X. So the number of successes. N is our sample size as always. P is our population proportion. And P hat is our sample proportion. Okay, so how do we find X? X is typically found by taking the number of samples you have times the value of that proportion. So for example, if 52% of 926 survey respondents responded yes to a question or to a survey, the actual number of those responses is calculated this way. So we have up here, we have x equals n times p hat. Our n is our sample size. And our p hat is the proportion of, or the percent of successes. Since these 52 people said yes. So we're saying 52%. So the first thing we have to do is convert that into decimals and multiply them. We get 481.52. Remember, whenever you deal with people, you cannot have a 0.52 of a person. So we have 482 that said that. So the rounding rule for these types are round up always. So that's how we find our success size p hat. Normal approximations. When we say normal approximation, we're trying to look at a solution based on a bell curve. And since we're dealing with portions, we remember we have those conditions that we have to have independent. Each event has to be independent. There has to be a fixed number of them. And in this case, they have to be binomial in nature, which means it's yes or no, on, off, good, bad. So we're looking at a binomial distribution. Where the only results can be yes, no, on, off, good, bad, and so on and so forth. So get the conditions is that it has to be independent, means each event doesn't influence on the others, has to be finite, has to be replicable, and our sample size must be large enough. And there we have another one of these terms that are very ambiguous in statistics. Of course, the larger you have of a sample, the better. The smaller you have is you're taking a lot more leadway of saying that this solution replicates the population solution. So that's why typically we use n is larger than 30. And be also that last section, we talked about sample size on how to figure out what exactly we need. I believe the formula was n equals z or t Z equals that over T. Oops, lights went off. Let's see, we have Z. Divided by our S or rho. Times our error. Or whatever proportioning structure we have. So that will be our minimum sample size we can use for our statistical analysis. In the notes I sent you all, we talk about equivalent methods. What that means is that when different methods produce similar results. For example, the p-value method is equivalent to the critical value method. Because they end up with the same conclusion. And sometimes they are similar to the critical value method. Or not critical value, that's just the confidence interval. So that's what, whenever we talk about equivalent methods, that's all we're talking about. Right. So out of these three methods, we have the p-value method, we have the critical value method, and we have the confidence interval. You notice we always start off with these two because those are the most common ones and the most accurate ones that we can get. These are used most frequently in testing claims. About a proportion. The confidence interval method, yes, we can use it, but it's not really used that often. So it's very, for the proportion, yes, but this one is if you're going to estimate it. This one is if you're going to test it. If you're going to test a claim. So this is when you're going to estimate a proportion. So that's the different modalities for different reasons. All right, so we're going to look at testing claims about a population proportion. So we're going to test for P. Remember the symbols that we use, the notations that we use, N is a sample size. P is the population proportion. P hat is a proportion is simply a ratio. So we have our results values in over N. This is, what do you call it? This ratio really is part over total. So this is of success. This is where all your X's are of success. To figure out of everything that fails, we use 1 minus P hat, which is 1 minus that. Okay, for testing the claims about proportion, we need simple random sampling, nothing exorbitant, nothing, because if it's simple, it's just automatically just I pick this. There's no thought behind it. Any other methods is you have to think about it. Okay, what are my conditions? I have to separate the groups, I have to redo them. They have to be of my binomial distribution, which means they have to be finite. You cannot have infinite samples. Finite number of samples. They have to be independent. In other words, they can't affect each other. Binomial in nature. That means it's either yes or no, good, bad, right, wrong. Results have to be the probability, I should say, of each sample must be the same. What I'm saying is the results have to be, the probability of the results have to be the same. So each one of them flipping of a coin. Each side has one of two chances. Rolling of a dice. So each side has one of 6 chances. And the last one that must.
Mr. Professor, you know, probability of each sample must be the sample. That must be the same.
Same. Yes. Too many letters. And last one. The value of our results have to be, for the success, have to be greater than 5. And for our failures has to be greater than 5 as well. Remember, it's a binomial distribution. So the number of samples we have times the probability of success has to be, the number of those occurring has to be greater than 5. The sample size times the number of probability of failure also has to be greater than 5. The standard deviation is that. All right. Just look. Oh, the difference between Z and T tests. When do we use which one? Remember, since we're Z or T. This is on the sheet I gave you yesterday also. Unknown. So if the standard deviation of the population is unknown and the sample size is bigger than 30, use a t-test. Population, it's not just deviation, it'd be variance also. Population information is known. But a rough breakdown of what we're doing here, of the when we use a Z or T testing. And these are called our test statistics. This is what we're going to use to compare it with our claim and everything else as that. Now, since we have a binomial distribution, there's only 2 possibilities. So we know what the population deviation of population sample is. So our numerator is p hat minus p. Remember, the p is the population proportion. And the bottom is n p over q over n. That's your z value. That is your test to statistic. That's what you use to, once you find the critical values, you can see whether you reject or fail to reject the null hypothesis. Okay, since we're dealing with proportions, we have to find the p-value. Right, so the way we have to assume first off that it's standard. It's a standard normal distribution. Why is that? Because it has to be a bell curve. That way we can determine whether it's one tail left or one tail right, or if it's a 2-tail test. So that's what we're gonna use. So these right here are our critical values. Those are the values that tell us at which point whether the values that differentiate the success or rejection of the hypothesis. So if our critical value is here and our p-value is here, then we fail to reject the null hypothesis. Or yeah, here's the null hypothesis is there. What's the difference between null hypothesis and alternate hypothesis? What's the difference between those two?
The difference is that the H1 does not contain equal to.
Equality. Yes, very good, very good. So it has to be the alternate hypothesis is you're claiming that there is definitely a change of something. So it's not equal to what's happening already. And the null hypothesis is what's happening already. So there's no real check. There's no real change going on. So let's look at this example here. Here's our claim. Most internet users utilize two-factor authentication. Most users use two-factor authentication. All right. So out of this, we found 52% responded yes to the survey. They use two-factor authentication in at least one of their studies or their online activities. Use this result to test the claim that most users use two factors, at least two factors authentication. All right, so this is our claim. Do we have to know the sample size? According to this, yes. So it's of 9, show here. Of the 926 respondents, we found that 52% use multi-factor. So looking at this information, requirement. Is it a finite number of samples? Yes, there are 926 people. Is it binomial in nature? Yes. The results can be either yes, they do, or no, they don't. Does each result have the same probability? Yes. Everybody has the same chance of answering yes or no. N times Q is greater than 5. Is that true? So what's our N? Our N is 926. The population probability, even though it's not stated in there, what is the population probability? Well, since it's a binomial, it's 50-50. So 50%, so we're looking at 0.5. Likewise, since that's 0.5, 1 minus P gives us 1 minus 0.5. So N times P is that greater than 5. So we have 926 times 0.5. Is that bigger than 5? Yeah, it's 463. Check. Same thing for the failure part. So you have to check these first before you go any further. Because if one of them is no, we can't use this method. We got to use something else. All right. Again, I didn't have a chance to because my computer still has to get replaced, so I didn't have a chance to download what do you call it, the software. But typically you enter the information into the computer, press 2 buttons, and it'll give you the answer. It'll spit it out. But if we do this manually, find the p-value. Because we have to know what the p-value is. What we know so far is our sample size is 926. The population proportion is 0.5. Do we know our sample proportions? It said 52% said yes. So since this is our population it's a 50% possible outcome for each trial. So that's our population. Our sample for this one is 52%. Or 0.52. So 1 minus 0.52 is 0.48. So now we have our sample proportions for success and a sample proportion failure. Everything else is calculated and given from the data. The only thing that we have to determine is our level of confidence. It is most common resorted that to 0.05. It's just a standard. Most of the articles and research you read, it'll always be 0.05, 0.05. And if it's a sure thing, you'll have a 0.01. If it's a long shot, then they'll have something like 0.1 or 0.2. So the bigger that number is, the less accurate it becomes. So that's a note whenever you read any statistical journals or research journals. So our first step. What's our claim? The claim is that most of the people use two-step authentication to protect their data. So two-factor authorization. We have to convert that. Convert to math. So it says most people. By definition, most people is a simple majority. If this is 50, then 51 is most people. It's more than that, so it's most. So we're looking at here for our experiment or example. We're saying that the population, because that we're making our claim of the population, not just of our sample, of our population. So we use P. And so we're saying that more people, most people, more than 50% use it. Step 2, so that's our success. What's our failure? Find the opposite. So it's opposite of greater than, less than, or equal to. Step 3. Now, since we have our claim and our other the alternative of that claim, we have define our null hypothesis and our alternate hypothesis from our two possibilities. And the difference is the alternate hypothesis will never have equal. Will never be equal. So our alternate hypothesis is our claim. The null hypothesis is that. So this is what we're going to be testing all of our results upon. Step 4. Determine your confidence level or the significance level. How sure are you going to be? This is your alpha. Step 5. We have to calculate our sample proportion, because we have to use our sample proportion to calculate the z-score in this example, because that's going to give us our quote unquote our p-value. So in ours, this is what the value of the sample supporting your claim. So this one says 52% of the people said yes, that they would use or do use multiple avenues, factoring method, authentication methods. So it's, once we find that, now we're in good shape, because now we have to compare this to the population. Find our test statistic. In this case, it's our z-score. Again, now here's another part. At this stage, on step 6, you have to determine, am I going to use a t-test or a z-test? And that's, again, that's, you have to understand the conditions of when you use it. If you have the population information, then you can use the z-score. If you don't know the population information, then you have to have sample bigger than 30 to use t. Okay, so find our test statistic. Our test statistic is the z-score, which is p hat minus p over the square root of n. We put the, again, that was calculate the formula we gave a while ago. So we need p hat, we need p, we need q, and we need n. N is a sample size. We know that's 926. P hat is our sample claim, the sample claim portion of our sample, which is 52%. P and Q, since they don't have hats, those are our population. So we figured out that these were 50-50. So we just plug everything in there. P hat is 0.52. P is 50. P is 50 or 0.5 times 0.5 times 926. Do this entire calculation. We'll get 125. What does this tell us? Well, first off, we know it's to the right of the mean. Because all of our sample, all our values from our tables will always be relative to the right side. If you want to calculate the left side, then just change the sign of these values, the z-scores. Because what this means is, this is at this point here, that's 1.25, and this point here is negative 1.25. Depending on which side of the test I'm looking at. Note also, the p hat is a sample proportion. which in our earlier sheet, we calculated as X over N. How many people said yes over how many people? So we have 482 over 496, 596, or 592, 526. And that comes out to be our p hat value. So here, now we got to determine if the distribution is a one tail left, one tail right, or two tail. For distribution of our test. So is it one tail left? Is it one tail right? It's over here. And if it's a two tail, since our z value was right, positive, we know it's a one tail. We're looking at a one tail right in our example here. And okay, our claim was most people use two-factor authentication. That's our claim. So here are people. This is the mean, so it's the middle of them. So most people, it would be on this side. We're not dealing with left. So that's why it tells us it's a one tail right test. Because we're looking for most people. It's people more than the average. All right, so we calculated our z value as 1.25. That's our critical value. That's the point where whether we keep or reject, where everything to the left of it is the null hypothesis, everything to the right of it is satisfying your hypothesis. So, okay, now what is our p-value? Oh. So looking at our table, table. Missing my table. There it is. So we're looking for 1.2 and 0.05. One point two is here. And
0.5987. No, sorry.
0.8944.
1.258944.
So what does that number represent?
It's 9.4%.
So 89.44% of the values are below that Z value. That's what it tells us. So how much area is over here? 1 minus our p-value, which is 1 minus 0.8944, makes it 0.1056. So our p-value, since we're looking for things on this side, this is the value that we have. Our p-value is 0.1056. What do we compare that to? I don't need that anymore. Compare the p-value to significance level. In our case, we use 0.05. So our value, 0.1056, is bigger than 0.05. Since it's in that part, we fail to reject HO. We can't say we reject HO, or we can't say we keep this or that, because there's not enough information known. Which it just says that all we can say here is we fail to reject HO means that we can't support the alternate hypothesis. Yeah. Let's see, do we have another example? Yeah, and the chart that I gave y'all in the sheets, it's a bell curve. Our critical value was at Z equals 1.25. This part here Our P here is 0.05. The Z because this is positive, this is negative, so the Z value is 0 here. So our P value was 1.056. Yeah, so this tells us the probability of this area is 0.156. The same stuff, the critical value method. Again, because the p-value and the critical values are the most common used. Again, we have our N was 926. We had 52% said yes. That's P hat. What else we know? The probability of success, or the population probability, is that. And we used as an alpha for the last one, we used 0.05. So pretty much everything else that we've done is the same. So step one, it satisfies all the conditions. So our claim is we want it to be greater than 0.5. So our HO and H1 less than equal to 0.5. We had step 2 and step 3. Let's see what we do. We use a confidence interval for that. And we know that our P hat is 52%. Yeah, so now everything else up to that point is the same. Step 6. We calculate our Z value. Our test statistic. And we get the same value, 1.25. And our alpha is 0.05. Now, what we have to do here, our test statistic with our critical values, we have to find the critical values, which is what the Z value is. Because remember, it's this line here is our critical value. So how do we find with 0.05? chart again. So we know this area is 0.05. Which means this whole area here is 0.95. So finding 0.95 in our table, it's between 0.95 is between 0.9495 and 0.505. So 0.95 is there. So to use a 0.95 area, our critical value is 1.645. 1.645. Our CV is our Z value, which is 1.645. In this one here, we use nothing but the table. We don't have to use a formula or anything. Okay, now, not a conclusion, but what do we know so far? Our test statistic is let me see if I do everything right here. We got our critical value there from 0.05. We found this area here. This is our critical region. Our test statistic is our Z value we calculated with the formula. And that gave us, last time gave us what? Oh. It gave us 1.25. Using our Z formula. We got 1.25. Since 1.25 doesn't fall in our critical region, is less than 1.645, doesn't fall in our critical region. So in other words, we fail to, I'm sorry. reject HO. So with this one, our critical value was 1.645. Our alpha was 0.05. The middle part is z equals 0 or p equals 0.5. And we got this value here. This is our test value. So it doesn't fall in the critical region. So we fail to reject the null hypothesis because it falls in the null hypothesis. Okay, let's look at the third method. So again, everything, this one's the same pretty much until we get to here. We calculate the z value the same with the formula. We just, our critical value is found differently. And the last method is the confidence interval method. So everything else same, 926. Then we have a 52% success rate. The probability is 0.5. Our alpha was 0.05. So since our alpha is 0, this is our significance level. What is our confidence level? Our interval is equal, since that's 0.05, we take whatever that is, double it, 0.10. So we're looking at a 90% confidence interval. That was from that chart we used yesterday. It said whatever our alpha is, double it, and that'll give us our confidence interval. Since it's 0.05, we double it, we get 0.1, so it's 90. If it was a 0.1, if we had a 0.1, then we double it, we get 0.2, which means we'd have a 0.80 or 80% confidence interval.
Confidence interval, yeah.
So that's what we did yesterday. So this will be very important for us there. So we'll use that. We use that. 52%. So we have to figure out our p hat. It's 52% of our population, which is 0.52, which means our q hat would be 1 minus p hat, which is 1 minus 0.52, which is 0.48. Confidence interval. Remember how we found the confidence interval last time? In last chapter? The one we looked at was like this. We dealt with means. It has the same format, but we're doing proportions now. So instead of mean, we use P. So we'll have plus our, I'm called error, and P minus our error. So what do we have to figure out? Look at your notes for chapter 7, section 1 or section 2 for proportion intervals. Actually, here it is. And on the thing I gave you yesterday, or the table, the confidence interval, one population. P hat minus error, P hat plus error, where the error is your z-score times the square root. So the error is your z-score times P hat Q hat over N. With our alpha being 0.05, what's our z value? We just found it a second ago. Since our alpha is 0.05, we know that the other side is 0.95. Then we have to go to find our value, 1.645. P hat was 0.52. So that makes Q hat 0.48 all over 926. Rounded up, we need 3 decimal places. Remember, the error rounding up rule is 1 more than what you start off with. So we have our P hat, which is 0.52 minus 0.028, less than P, less than 0.5 plus 0.028. So this is going to be 0.49. 2. And this is gonna be 0.5. This is 0.52. So that is 0.548. So that is our confidence interval. So what does this tell us? Remember, we're trying to estimate the population. What is this? We figured out that we have a 0.5. So what's the likelihood that this falls between there? Well, it's very good because the likelihood of this one falling.
Yeah, we can say that 0.492 between 0.492 and 0.548.
Right. So there is a likelihood of it falling in there. So what does that tell us? So since it satisfies this condition,
So we accept.
yeah, in other words, we can't conclude that we can't predict that they're going to do that. That's going to be more than expected. So since it falls in this interval, that's what was naturally expected. So we can't say that most people would support two-factor authentication because it falls into what it's supposed to be already. All right, now we're looking at, well, unfortunately, the other methods, the alternate methods, we can talk about, but we can't really do because those require the use of some sort of program. So it's not, I don't know why they threw it in there because you have to use some sort of, and then when you do that, all you do is just plug the values in there and see what you get. And the only calculations that you do is for the z-score or your test statistic, which is z equals p hat minus p times q. Remember, on the denominator, it's of the population, not the sample. This is for your test statistic. And then whatever method is, whatever your program gives you as a solution, then you compare it to this. Yeah, there's not much we can do with that. All right, so that does it for 8.2. Let me close this and open up 8.3.